give an overview of the FAA and some data points around the FAA's mission, the data the FAA provides to provide the framing of what are the surveillance systems that we can bring to bear, or there's data around those sensors, as well as to frame the limitations of those. I know Sean talked about some of the data points that are used and being integrated. So hopefully this will give you an overview of the FAA's mission as well as those data points. Next slide, please. So the FAA's mission is quite large and complex. By a factor of 2, we operate more commercial aircraft than any other country. I think we're second only to Australia in total airspace, but largely because Australia has a very large oceanic volume that they're responsible for managing. So it is a very complex, very large national airspace system. We have over 14,000 controllers, 520 air traffic control towers, which are located at the highest density of airports, and I'll refer to those as towers in subsequent slides. We have 147 what we call terminal radar approach controls, or TRACONs, and those are manned control facilities at the high and medium density airports around the nation, as well as 21 air route traffic control centers, which manage the control of air traffic in the en route environment. There's over 19,000 airports, over 5,000 of those are associated public airports, with the remaining 14,000 plus private airports. Next slide, please. So the FAA's mission is primarily around safe and efficient control of manned aircraft. That has been our historical mission, and it remains our primary mission. Certainly as we talk about new entrants with UASs and advanced air mobility and some of those things, there will be an evolution of the FAA's mission to include safe operation of the NAS with those new entrants. But the architecture and design of the NAS is geared around safe and efficient control of aircraft and manned aircraft. Certainly the commercial aspect, the commercial flights are a primary focus of the agency. We certainly support general aviation and flights as well. But again, our mission is around manned aircraft and safe and efficient operation of those. By the numbers, over 16 million flights yearly, 5,400 flights at peak at the peak time of any given day, 45,000 daily flights, 25 million GA flight hours per year. Very large, very complex operation that we're responsible for managing. We certainly provide a significant contribution for that service to the nation in the form of product toward a GDP. Next slide. So as we get into the discussion of surveillance services, I want to provide a little bit of framework around the categorization of our surveillance services, and we primarily break those into two bodies. The cooperative surveillance, which is defined by a sensor that's avionics or equipment on board the aircraft that works in conjunction with ground-based sensors. The non-cooperative surveillance is independent. This is basically the classic radar. RF energy is transmitted out, reflects off the target, and we receive that signal, and from that return we can determine where that aircraft is. Typically these cooperative and non-cooperative sensors are co-located together, the cooperative mounted on top of the non-cooperative radar. So from a data perspective, I think in this panel, in the study, I think that the cooperative sensors, those are neither unknown or anomalous. So for the purposes of this briefing or the rest of this briefing, I'm going to focus on the non-cooperative aspect. Next slide, please. So again, from a standpoint of the mission of the FAA, is primarily around manned aircraft, and I think that serves as an important framework for the data points and the type of data that we can bring to bear for this panel. So we break our systems and the design of the systems into different types of systems. So we have short-range radars, which are typically located at the high and medium density airports. And those operate from a range, they have a detection range of between 40 and 60 miles and an altitude detection capability of about 24,000 feet. The long-range radar systems have a detection range of 2 to 250 nautical miles with altitude detection up to 100,000 feet. So that provides the basic, the framework for those. I will mention the Automatic Dependent Surveillance Broadcast, or ADS-B, only from a context that does serve as a primary data source and a preferred data source for the management of the airspace system, but it is a cooperative system, and for the purposes of the next slides as I get into the discussion of the coverage and the type of detection for those non-cooperative targets, it is not considered as part of those. And also surface surveillance is also something that we provide, but again, for the purpose of the study, I only include those for just a completeness perspective. The one final point, as I talk about manned aircraft and primary mission for the drones and balloons and things of that nature, their basic premise is to operate in a not to interfere basis, that they are not to interfere with manned operations. And that's a fundamental aspect as we talk to the data and what we can and can't detect with respect to those non-manned systems. Next slide, please. Realizing this is an eye chart, I wanted to provide just a graphical or pictorial depiction of where our sensors are located. The green, blue, and pink balloons, if you will, represent our short-range radars. Those are located at airports. Those are where those are sited. The two reddish balloons, they have letters in them, a 4 and a C. Those represent our long-range radars, the ARSR-4s and CARSR systems that are used in the context of both from an air traffic control perspective as well as for a national defense and homeland security mission. And the perimeter, the ARSR-4s are located around the perimeter of the country, equally spaced, and the CARSR systems are located on the interior of the U.S. I will point out that this only depicts the CONUS. There are systems, ATC, both short-range and long-range systems, Hawaii, Alaska, and Caribbean. Those are not depicted here. I didn't think they were necessary for the purpose of understanding the surveillance. And I will also point out that both for this slide and the subsequent coverage slide, I do not talk to any classified DoD or DHA systems that are in operation. Okay, next slide, please. So what can the FAA detect and surveil, what can we not? This slide gives you a by altitude slice of what it is that we can detect. So if you look at the square that's labeled 1,000-foot AGL, that depicts by sensor for an aircraft that is 1,000 feet in altitude, what is the range at which we can detect that aircraft. And so on, as you get higher in altitude, or higher in altitude, you can detect it at further range. And that's basically a phenomenon of the curvature of the Earth and the line of sight aspect of these radar systems. So pretty good coverage across the U.S. at 10,000 feet and above. This is a mathematical model based of a pure line of sight as well as some geographical screening. As you can see in the western part of the U.S., there is screening due to the mountains and those sensors. Need to take a little bit of time and talk about the nature of the targets. These line of sight models represent an input of a target that is 1 square meter. So think of a sphere of 1 meter in diameter. That's the assumption that goes into these models. So if you think about that in the context of other forms or aircraft, a 4th generation F-15 or F-18 is in the proximity of about 1 square meter, perhaps a little bit larger. A large airliner is perhaps 100 square meters. A small UAS is perhaps one or a 0.01 square meter. So the range of these detections, or the size and the ability to detect these targets from an F-15 large airliner, 100 times larger in size, a drone 100 times smaller in size. So the detection and the surveillance capability really largely depends in part to the target that we're talking about and the ability to surveil that target. All right, next slide. So I do include this ADS-B coverage slide just to give a context of, from a cooperative perspective, there is very good coverage across the U.S. to 1,500 feet above ground level. So this provides a context of when we look at the data and start getting a discussion of what it is we can detect. This will certainly be, for those cooperative aircraft that have ADS-B, we could certainly detect those to a pretty low altitude across the U.S. All right, a couple of data points. I think I know Sean certainly talked about some of the data points, and I can provide a little bit of insight from an FAA perspective. Drones are a pretty significant challenge. There's 880,000 registered drones in the U.S. Small drones, I should say, Part 107 drones. Many tens of thousands of those are operated on a daily basis by commercial operators. It's not clear how many private drone operators are taking their drone up for a quick flight. But as I said earlier, those are regulated they're regulated to operate below 400 feet in altitude. So again, it's the drone aspect is for those small drones in particular, and as well as all classes of drones. There are regulatory restrictions to where they can and cannot fly, basically avoiding and not interfering with manned aircraft operations. Second data point, we talked about balloons. The Weather Service, we know on 92 weather stations that release balloons twice a day. At 6 a.m. and 0000 Zulu and 1200 Zulu. Typically 2-hour duration. They fly up to 100,000 feet where the envelope bursts and then the payload descends back to Earth. So certainly, at least 184 balloon flights daily in the NASA. Not to consider universities and hobbyist balloons that may be launched, but those are typically small in size. And finally, Sean did talk about UAPs and FAA data. A couple of data points that we do report. There is a process by which air traffic controllers can report UAP sightings or events. Historically, those have been in the range of about 3 to 5 reports per month that have been reported. We did see an uptick of reports in August of 22 that went up to about 8 to 10, perhaps due to Starlink launches. And finally, with the Chinese weather or the Chinese balloon incident in February, we did see a significant uptick, and there's like 68 UAP reports that started in February, and we've seen a large number, subsequent to that. I think that's all I had. Any questions?
Do you want to take the question? It's easy. Actually, you can choose the questioners. It's easier from your angle than from mine.
All right, Walter.
Yeah, so two questions about the radar data coverage. First one is, do you retain any of the data, or is it just cycled over as?
There is a long-term retention of data. I can't recall exactly how long we retain that. There's certainly a requirement from a retention from a legal perspective. Yeah, exactly. But I do know there is some periodicity measured in a term of months.
Is it retained in terms of like the raw radar, or is some processed form of data that's retained?
I believe it's a processed form of data that is what was displayed on the, whether it's an Indian route ERAM system or the STAR system.
And then the other question is, for the radars, are they operated in any sort of a tasked mode, or are they constant search mode?
The current systems in our inventory, just they're fixed face and they just rotate at either
Okay.
12 RPM or 5 RPM, depending on whether it's an en route or a terminal surveillance
Okay, thanks.
requirement.